Let's go back to the second law of thermodynamics. We will recall that the entropy change for a spontaneous process is positive. That is, entropy increases. A more precise statement of the second law is, in any spontaneous process, the total entropy, or the entropy of the universe, increases. Our earlier examples have shown this. Some spontaneous changes seem to contradict the second law. When water condenses on an ice-filled glass, does entropy decrease? If you think about it, the system does seem to lose entropy. The disorderly gas molecules in water vapor become more orderly in the liquid phase. To view this event properly, though, we have to look at the effect on the surroundings. Gaseous water molecules give up energy on becoming liquid. This energy is transferred to other molecules in the air, resulting in a greater movement among the gas molecules. On the whole, therefore, the entropy of the system and the surroundings has increased. The energy of the system itself, the condensed water molecules, has decreased. Can we explain the entropy changes in a system that loses energy, such as burning fuel? A system that loses energy to its surroundings transfers that energy to the molecules in the surroundings, which begin to move faster. This results in greater entropy of the surroundings. For irreversible or spontaneous processes to occur, it is the total entropy of the surroundings and system that must increase, not just that of the system. If the change causes a larger disorder in the environment, then the process will be spontaneous. Entropy is a thermodynamic quantity that is a measure of randomness or disorder of a system. It is given the symbol S. We use it to describe atoms and molecules. You can also use it in a general way to describe your classrooms after the students have left. Or maybe sometimes even while they're there. Let's look at these marbles and boxes. The marbles represent particles. We will put them in various combinations into two boxes. Start with two marbles. These can be distributed in four ways. There is only one way of putting two marbles in the red box. Two ways of putting the marbles in separate boxes. Now, add two more marbles. There are now 16 possible arrangements for putting four marbles into two boxes. There's just one way of arranging all the marbles in the red box. As the number of marbles increases, the number of different arrangements of marbles in boxes also increases. We say that a disorder or randomness or entropy of the system increases. These observations hold true whether we're talking about a few marbles or an Avogadro number of molecules. Hello, I'm Ramon Miranda, your host for Chemistry in Action. In the last episode, we saw that enthalpies of reaction tell us whether energy is absorbed or given off in the course of a chemical reaction. For spontaneous reactions, we said that energy is usually given off. There is also a tendency for the entropy or disorder of the system to increase for these types of reactions. In today's lesson, we will answer two questions. How do enthalpy and entropy affect the spontaneity of a reaction? And how do we know if a reaction will be spontaneous? Before we answer those questions, bring out the boxes and marbles I asked you to bring for today while we pause for some reminders. If entropies of substances under given conditions can be measured, then it is also possible to measure the change of entropy in a substance as it goes from one state to another. The entropy of a substance changes with temperature. It increases as a substance changes from a solid to a liquid to a gas. As a general rule, entropy also increases when a solid or liquid is dissolved in water. Entropy decreases when a gas is dissolved in water. Likewise, the formation of a greater number of gaseous products is accompanied by an increase in entropy. The dissociation of nitrogen pentoxide into nitrogen dioxide gas and oxygen gas illustrates this. There are no gas molecules on the reactant side, but there are 2 moles of NO2 gas and 1/2 mole of O2 gas on the product side. An example is the complete combustion of ethyl alcohol. You can count 3 gas molecules on the reactant side and 5 gas molecules on the product side. We account for the increase in entropy in terms of the more random and disorderly movement of molecules as matter changes phases. But how do we calculate entropy change for a chemical reaction? Just like enthalpy change, the change in entropy is a difference between the total entropies of the products and the total entropies of the reactants. Tables of entropies are useful in making these calculations. When we return, we will discuss what the numbers for delta S mean and how we make use of them. Systems that undergo a spontaneous change tend toward a state of minimum energy and maximum entropy. The overall change in free energy, a combination of enthalpy and entropy changes in a reaction, determines whether a reaction will take place or not at all. A change is spontaneous when the value of the free energy change is negative. A change is non-spontaneous when the value of the free energy change is positive. And that answers the question, how do we predict the spontaneity of chemical changes? Now, for the next question, how long will it take for a reaction to take place? In other words, what is the rate of a chemical reaction? Be with us next lesson as we dip into the branch of chemistry called kinetics, the study of chemical reaction rates. Until then, this is your host, Ramon Miranda, wishing you a good day. Meanwhile, here's what we've learned so far. Let's take some moments to review what we've learned so far in this part of the lesson. In any spontaneous process, the total entropy of the universe increases. For spontaneous processes, the total entropy of the surroundings and the system must increase. The sign of delta G tells us the direction of spontaneous change in a system. At the equilibrium temperature, the tendency toward minimum energy and maximum disorder are balanced. The discussion on this order leads us to the second law of thermodynamics. A spontaneous change is accompanied by an increase in entropy. Recall the definition of spontaneous change. A spontaneous change occurs on its own without help from a continuing outside force. Many of the spontaneous changes around us result in a greater disorder of the system. This tendency to greater disorder explains why we never see gas molecules collecting at one end of a container, or why a solution of food coloring does not separate into its pure components. In the case of burning paper, the tendency toward greater disorder contributes to the spontaneity of this exothermic reaction. The gaseous products, carbon dioxide and water vapor, diffuse readily into the surrounding air. If we say that entropy increases or decreases, does it mean that it is a measurable quantity? Or is it something vague that we can only describe qualitatively? The third law of thermodynamics gives us the answer. It states, any pure crystalline substance has zero entropy at absolute zero. At this temperature, the particles of a pure crystal are perfectly ordered and have minimum motion. Above this temperature, entropies of substances can be measured. They are usually reported for a temperature of 25 degrees Celsius or 298 Kelvin. This is the case for graphite and diamond. They have very different properties, but it's less obvious that they are just two different forms of carbon. Lower entropies mean less disorder. Diamond, with a lower entropy, has a more ordered structure than graphite. In diamond, every carbon is bound to 4 other carbon atoms, producing an intricate three-dimensional network of atoms. In graphite, the carbon atoms are in a two-dimensional hexagonal arrangement in planes. These planes are stacked on each other and easily slide past each other when the slightest pressure is exerted. This is why graphite is such a soft substance. Pencil leads are made of graphite, not lead. The entropies of many other substances are listed in tables of entropies found in chemical handbooks. This is how we tell whether reactions are spontaneous or not. Let's take some moments to review what we've learned so far in this part of the lesson. Try to imagine the energy changes that take place in our bodies as we breathe, move, and work. The energy released from metabolic reactions within the body can be used to do various kinds of work. However, the conversion of energy to work is never 100% efficient. For example, we use only about 2/3 of the energy liberated by the oxidation of glucose. The energy not converted into work is classified as unavailable energy. We can express unavailable energy as a product of temperature and entropy, T times S. The available or useful energy is called the Gibbs free energy and given the symbol G. These two quantities can be combined in a single equation. H is the enthalpy of the system and is equal to the sum of its available and unavailable energy. The equation may be rearranged into another form. G equals H minus T times S, where T is the absolute temperature of the system. The equation for the change in free energy, delta G equals delta H minus T delta S, is the form useful to us for predicting the direction of change for a system. The sign of delta G tells us the direction of spontaneous change in the system. At constant temperature and pressure, a change is spontaneous if delta G is negative. A change is non-spontaneous if delta G is positive. If delta G is zero, then the system is said to be in equilibrium. The four possible combinations of the signs of delta H and T delta S are summarized in this table. Take a spontaneous reaction such as the oxidation of glucose in living cells. It is an exothermic reaction and delta H is negative. The entropy is positive due to increased disorder when 1 mole of glucose combines with oxygen to form 6 moles of water. The combination of negative delta H and positive delta S always results in a negative delta G. Our conclusion: the reaction is spontaneous at all temperatures, and the reverse is non-spontaneous. Consider the formation of ethylene, C2H4, from the elements carbon and hydrogen. Here, delta H is positive. It is an endothermic reaction. Delta S is negative. You can see that entropy decreases in the process because there are 2 molecules of gas on the reactant side and only 1 molecule of gas on the product side. At 298 Kelvin, the calculated value for delta G is positive 68.1 kilojoules. Delta G is large and positive, therefore it is not a spontaneous reaction. Preparing ethylene from its elements requires a large input of energy and is not the preferred route. Ethylene is produced commercially by cracking, a process in which very large hydrocarbon molecules are broken down into smaller ones by the application of heat. What happens when the tendency to lose energy, that is, negative delta H, and the tendency to increase disorder, that is, a positive delta S, oppose each other? It depends on the temperature of the system. At the so-called crossover equilibrium temperature, the tendency toward minimum energy and the tendency toward maximum disorder balance each other. At this point, delta G is zero. Below or above the crossover temperature, the reaction will be either spontaneous or non-spontaneous, depending on the temperature of the system. For the melting of ice, the crossover temperature calculated from delta H and delta S is 273 Kelvin or 0 degrees Celsius. This is a melting point of water at 1 atmosphere pressure. We all know that ice melts above 0 degrees and remains frozen below this temperature. From our calculations, we see that above 0 degrees or 273 Kelvin, delta G is negative. The process is spontaneous. Below 273 Kelvin, delta G is positive and the process is non-spontaneous. This is how we tell whether reactions are spontaneous or not.